Hey guys, so in this video I want to keep talking about wave functions, but in particular a special type of wave function. Right? So to start, let's remember that we defined a wave function, or we figured out a wave function that ended up being very helpful to us. Phi sub a of x, right? Where this is the wave function with a definite value, right? It has a definite x position equal to a, right? And so this wave function, sorry, I didn't mean to put that third line there. So phi sub a of x, we know, is delta of x minus a, right? Where we have the direct delta function, and this is, of course, the same as delta of a minus x, right? And so now I want to find, well, we know position. Well, we've got another very important quantity in physics, which is momentum. And I want to find a function with a definite value of momentum, phi sub p of x, right? And it turns out we can do this, but it's equivalent to also find a wave function with a definite wave number, right? And if you remember our de Broglie relations, p equals h over lambda, right, which is the same as h bar k, where h and h bar are just constants. It's the Planck's constant and the reduced Planck's constant, and the k is just 2 pi over lambda, right? And so just like momentum is an observable quantity, right? The wave number also is an observable quantity. Right? And so if we have a particle, we can observe its wave number, and that gives us its momentum. So there's no real reason, to distinguish between phi sub p and phi sub k. That it's the same thing, right? If we know the wave number, we know the momentum, and if we know the momentum, we know the wave number. So it turns out just to be a question of the convention. Which one do most people write? And also, which one is the easiest to write, is the neatest? And in terms of both of those questions, we have phi sub k of x, which is going to be the function that we're really going to be looking at. But a wave function with a definite momentum, right? This is wave function, I'll abbreviate WF, with a definite momentum, right? Definite momentum, which is p equals h bar k, right? So this is the wave function with a definite momentum, and I'll call it that, but we're going to write it in terms of k instead of p. That just gets, it just makes things a little bit cleaner, and so that's what we're going to be doing. The other thing is this video is going to really show you why we call it the wave function, right? Because now we're really talking about waves. Now we're including that wave-particle duality that's encompassed in the de Broglie relations, right? Where a particle can be modeled as a wave, and the wave number of that wave is proportional to its momentum, and vice versa. So for this, right, well, we know some functions with a definite wave number. We know two of them, actually. We know sine of kx, right, and cosine of kx. And make sure you've reviewed my video on mechanical waves in section 0 if this is not super familiar to you. And I'll link that in the description. Right, and so sine of kx and cosine of kx, they're both just waves with a definite wave number, definite wavelength. In any combination, right, sine of kx plus 2 cosine kx, or right, any combination is still just going to give you a wave with a definite wave number, right? And so right now we're going to look at a particular combination of sines and cosines, and that's going to be e to the I kx. Hopefully you can also review that video on complex exponentials that I will also link. And we know e to the I kx is cosine kx plus I sine kx. And this is that function that we're going to use to represent just a function with a definite wave number. Right? So this is equal to, oh, didn't want to use a different color there. There we go. Equals e to the I k x, right? And there's actually a really nice reason why we are using this as opposed to the sines and the cosines, right? And so the reason I'll give you here is, say this is a straight line. This is like our, this goes out. This is our x-axis. We release a particle with a definite momentum, right? We can't release it at a particular point because, hopefully, as you know with the uncertainty principle, if you release a particle with a definite momentum, you can have no idea what its position is, right? And so, if we just release a particle randomly anywhere, right, then if we release a particle randomly anywhere with a definite momentum or definite wave number, it wouldn't make sense to say that it has like a sine wave pattern saying that it has to be 0 here and 0 here, or a cosine wave pattern where it would have to be 0 there and 0 there and 0 there, right? That wouldn't really make sense to say, right, just out of symmetry. Hopefully that would make sense. We just release a particle to be free wherever it wants to be. We can't really say, oh, but it can't be, it's most probable to be here, there, if we just release it in free space. There will be a time, actually, that we will see in section 4 that we can actually, say it has to be 0 here, 0 here. But that's not releasing it in free space. That's putting some constraints on, we'd have to physically put some constraints on where the particle could be. Without any constraints, it wouldn't make any sense to just have a free particle with some momentum and tell it, that give it this pattern, right? And in fact, e to the ikx, if we look at the probability density, this is really important. We look at the probability density, which is the norm squared so the probability density rho of x, and again, this is not normalized, and I'll get to that in a minute. So rho of x being the norm squared of e to the ikx. Well, we know the norm, the absolute value of e to the ikx is 1, right? So the norm squared is 1, right? And that just means it's independent of x. The probability, if we release a particle of with some momentum and we just release it, right, it's just as likely to be anywhere, which makes sense also given the uncertainty principle, right? And so, right, the probability density would look like that if this is the x-axis. This is rho of x, right? And now we want to make it so that the area under this from negative infinity to infinity is equal to 1. That doesn't seem really possible at all, right? And hopefully you can see that it's not, because if we do this integral, we'll get infinity, right? And so that tells you that it's impossible to have a particle with a definite momentum, which should also make sense, because it wouldn't really make sense to have a particle that you have no idea where it is. It could be anywhere in the universe, right? Or even if you knew it to exact precision, couldn't even fit just in the universe. It could be absolutely anywhere, right? From negative infinity to to infinity, right? So that makes no sense at all. So it makes sense that we can't actually have a wave function like that, just like we can't have a wave function with a definite value of position, that the delta function, delta of x minus a, is not normalized. And we talked about that either last video or a few videos ago, that it's actually good that those aren't normalized, because those are not actually sensible physical functions. But if we take a continuous superposition of all of them, then they become actual, reasonable things to work with, right? And the last thing I'm going to do here, so hopefully this tells you why e to the ikx is a good function to use for this. And the last thing I'm going to do here is I'm just going to add a constant factor divided by the square root of 2 pi. Right? And this doesn't change anything about this being a wave. This is sort of like a normalization factor, kind of, even though we know the function can't be normalized. Um, it does give us an interesting consequences mathematically later, right? So again, it doesn't really matter. We could just say, this is O2 delta of x minus a. It doesn't change the nature of the function at all. This constant factor is just going to make our math easier later. So we're just gonna call it there. Um, and I'll explain to you in actually just a minute or just a few minutes of why that factor is there, right? And so now that we've gotten here, I'm gonna erase some of this. We want to express, right? We know we can express psi of x. To go into blue here, we know we can express psi of x into a superposition, right? So the sum over all, this is like the sum, the integral over all possible values of this quantity, right? Because we know it's we know that this is c sub q phi sub q of x dq, right? Well, now we're going to specifically talk about the observable quantity k, right? So this is going to be c sub k phi sub k of x dk, right? But we know what phi sub k of x is. We know that this is e to the I kx, and then our 1 over 2 pi factor. I'm just going to bring it outside the integral. Right? Hopefully you can see that. I can actually redraw some of that. So psi of x equals 1 over root 2 pi. Right, and then this integral, right? So we could just bring that 1 over root 2 pi there. It has the same form, right? And so now, right, we also know from our from one of our postulates of quantum mechanics that we know that ck, right, is equal to the inner product of phi sub k of x times psi of x, right? And so we can express this as c sub k equals the integral from negative infinity to infinity. I'm going to leave space for our 1 over root 2 pi here, because we will eventually get back to it. And then, so this is phi sub k of x, right, which is this, but taking the complex conjugate, right? And we can note right here that phi star sub k of x, right? The complex conjugate of a complex exponential, we know from that video on complex exponentials, is e to the minus ikx over root 2 pi, right? Because then that function just carries over, right? So now we have, we have e to the minus ikx. We've got our 1 over root 2 pi, right? Which we could just put here, but it's more standard to write it out here, times psi of x dx, right? And again, here we're integrating over k, so k won't appear in our answer here. Here we're integrating over x, so x won't appear in our answer, which makes sense. C sub k is the probability amplitude, right? The norm squared is the probability density of having k, of having the wave number k. And psi of x, right, does not have any k in it, right? And so these are our big equations. I'm going to rewrite them a little bit as we develop a little bit more in this video. All right. So these are often referred to as the Fourier transformations. The F-O-U-R-I-E-R, Fourier transformations. Actually, this one is often referred to the Fourier transformation. This one would be the inverse Fourier transformation. Not exactly in these forms, but in a minute we're going to get to the form that you'll often see, at least in physics, the Fourier transformation. I should note, Fourier transformations are very important in math, engineering, and physics. And in all three of those, they're written completely differently. So these are the way that we write it in physics, but you will see it if you take an engineering class. You'll see it written in a different way. If you take it in a math class, you'll usually see it in a different way. So it sort of depends on what you're using it for, but it turns out to be incredibly useful, as you will see in just in quantum mechanics. All right, and so now, right, we've expressed the wave function psi of x is the wave function in the x basis, right? We talked about that in, I believe, the last video, right? And so now, why can't we find in the k basis, right? Just like this is sort of like in the color basis, and now we want to go to the hardness basis to find the state vector, or the state vector, the wave function, right? And when we write it in this form, in the k basis, we're going to add a little tilde on top of it. And the tilde just means that we are looking at it in the k basis, right? And so sine tilde of k, right, is how we're going to write it. Right? And now we're not going to use k. Instead of using k as, the thing we sum over, right? Just like how we had in the x basis, where we were looking at wave functions with a definite, right? We had phi sub a of x, right? We can't have phi sub k of k, right? It would be phi tilde, right? We can't have that, right? That wouldn't make sense. That's a wave function in the k basis with the definite value of k being k. That's using the symbol for too many different meanings. So, sorry, I meant to erase this. So we're going to call it b instead. Right? So phi tilde sub b, okay, has a definite value of the wave number k equals b, right? And so now we can write this as a superposition, right? Summing over all possible values of b, right? This is our q, right? And so we have, this is c sub b times phi sub b of k, except this is phi tilde sub b of k, right? db, summing over b, taking the integral, right? Summing over taking the integral depends on if you're looking continuous or discrete, right? And so now, right? Well, what is this? What is phi tilde sub b of k? Well, just like it was in position space, right? If we think about it, this would be a delta function, delta of k minus b, which is the same as delta of b minus k, right? And if what does this mean, right? This is a wave function. If we write it in the k basis, where this is the k axis, right? And it peaks at k equals b right here, right? And so this looks like it would be a wave function in the k basis with the definite value of b, right? With a definite wave number, right? It wouldn't look like a wave anymore because we're not looking at it in the x basis. We're looking at it in the k basis. So hopefully this makes sense. It's a little bit weird to think about, graphing it in the k basis. But if you can wrap your head around that, it's the same logic that we used for having the Dirac delta function be the be phi sub a of x, right? Delta of x minus a. So hopefully you can sort of see how this makes sense, right? And so now we know that this is the integral from negative infinity to infinity c sub b delta of k minus b db, right? And now we know this trick all too well. We can turn this into a k and bring it outside the integral, and then it is the remaining integral is equal to 1, and so this is c sub k. Right? So this is exactly what we did with position, right? So we showed that c sub k, this probability amplitude, that's the wave function expressed in the k basis. Just like we showed that c sub x was just the wave function, right? And so now we can use this. We know that the probability density of having a wave number k, right, is the norm squared of phi tilde of k, right? And this makes sense. And just remember, when we're taking the probability density of k, it's not per unit length, it's per unit wave number, right? So the probability between k, k1 and k2 is the integral from k1 to k2 of rho of k dk, right? It's not dx, right? Because we're integrating in k space, right? This is what we call k space. It's the wave number basis, and so it's just called k space, right? And this is also the momentum basis. Momentum basis, k space, same thing. Right? It's just the difference will be just a few factors, just factors of h bar. That I'm not going to get into that too much. Just so you know, just making sure we're clear why we're doing this. It's because if we know the wave number, we know the momentum, and that's important in physics, knowing the momentum. Okay, so the last thing I want to do in this video is fully show you the Fourier transforms. Fourier transformations. And so this is going to be just a little bit. So now going back to how we wrote this before with CK, I'm actually going to write our inverse Fourier transformation, right? Which was, we knew it was CK. Hopefully you have them written down. CK is the integral from negative infinity to infinity. We've got that 1 over root 2 pi. And then we had we had e to the minus ikx times psi of x dx, right? And actually, I'm going to swap these. I'm just gonna exchange sides, and you'll see why, right? And then I'm gonna bring this back in. So I'm gonna rewrite this in a interesting way that you'll kind of see why I'm doing this. So right, so psi tilde of k is equal to the integral from negative infinity to infinity of psi of x times e to the minus ikx over root 2 pi dx. Now this may look like a superposition, right? Where this is, we have right here, this would be our phi tilde of sub x, okay? Right? This is, and this is just cx, right? And so our q would be x, right? So this is just a superposition, right? We originally came at it as this is an inner product, right? It's the inner product, but this is also a superposition of the wave functions with a definite value of position in momentum space, in k space. So, right, this shows you that in k space, the function with a definite position, x, in k space, the wave function with a definite position is 1 over root 2 pi times e to the minus ikx. This is an important one. Make sure to write it down. Right? So this is pretty cool, right? That we were just using the logic with Fourier transformations, able to figure out, or the logic with this inner product and the wave function in momentum space, we're able to figure out the wave function in momentum space with a definite value of position, right? And hopefully, again, you see why this is the superposition, because this is Cx, and we know that psi in any basis can be written from, this is the integral from negative infinity to infinity of Cq phi q, phi q, and then it does not have to be of x, right? And so phi q dq, right? And if we were writing this in the k-space basis, right, we just have the tildes that show that we're working in the k basis, right? And now, if we just sort of compare this, well, psi of x we know is c of x, right? And then for this integral to be true, right, this other thing has to be phi tilde sub q, right? So hopefully this makes sense. And so this is a superposition. And now we can show, right, we know that Cx, given the superposition, we know Cx, which is the same as psi of x, has to be the inner product of phi tilde sub k, or phi tilde sub x of k times psi tilde of k. Right? We know this. This is just one of our postulates of quantum mechanics. And this is, if we just do this integral, this is the integral from negative infinity to infinity of, well, we take the complex conjugate of this, the complex conjugate of that, right? We take the complex conjugate is just going to be 1 over root 2 pi e to the ikx, right? We just did that before, the other way around, right? So this is the integral from negative infinity to infinity of, I'll have this 1 over root 2 pi out here, e to the ikx times psi tilde of k dk. Well, that looks familiar, right? That is the Fourier transform that we just had, right? Where we wrote this as c sub k, right? But they're the same thing. So, rewriting, we have our two Fourier transforms again. So, what I did here was subtle, but it's really cool. I originally got this one from taking a superposition, and I got this one from taking an inner product. Or, sorry, I got this one from taking an inner product. But then I figured out that I could have also gotten this one from taking a superposition and gotten this one from taking an inner product, the other way around, right? And so the last thing I want to do here is recap this, because it may seem a bit confusing, which is perfectly understandable. So let's go for a quick recap. So we know that psi of x, actually I'm going to use a little bit of more lively color here. Psi of x is the superposition, right, from negative infinity to infinity. That we can express this as a superposition of psi tilde of k, where this is c k, right, e to the ikx over root 2 pi dk. And I'm actually going to put this in a different color. I'll put this in orange. So this is ck, and this is phi sub k of x, right? And so this is a superposition. Right? And then we did the inner product, where we knew that ck, which is psi tilde of k, is equal to the sum from, or the integral from negative infinity to infinity, right, of, let's see, I'll just write it like this: psi of x times e to the minus ikx over root 2 pi. Right? And this is, here we have, this is psi of x, right? Oh, and I forgot our dx. So this is psi of x. This is phi sub k of x complex conjugate, right? And so this is our inner product. And I have to write the other two a little bit smaller. So I'm going to write them in a new color. So now we know psi tilde of k is the integral from negative infinity to infinity of psi of x, right, times e to the I minus ikx over root 2 pi dx. No, I just wrote the same thing in a different color, right? But here, this is our c sub x, and this is our phi tilde sub x of k, right? And so this is a superposition. And finally, right, we know that cx, I'll write this in green again, cx, right, which is psi of x, is equal to the integral from negative infinity to infinity of psi tilde of k times e to the ikx over root 2 pi dk, right? Where I ran out of room to write this, but we have, let's see if I can squeeze it in. This is our c sub k, right? And this, this is our psi tilde of k, right? That's exactly what we want it to be. And this is our phi tilde of x star. Okay, I know this is a lot of symbols, but this is our wave function in k space with a definite position complex conjugate, right? And so this is a inner product. Right? And so this is, not a lot of textbooks will show it like this, but I wanted to show it. It's kind of beautiful, right? You get the same equations in position space and momentum space either by doing a superposition, by doing an inner product. And this is actually a really good sign. This shows that everything is fitting together perfectly, right? everything is consistent. It's giving us the same equation, and actually it's specifically consistent because c sub k equals psi tilde of k, right? Otherwise, if we didn't have this and if we didn't have this, we would have been able to get it anyways from the superposition, right? So again, hopefully this makes sense. If that last point didn't make sense, just ignore it. It's not important at all. So yeah, this is the Fourier transform, right? And so this is going to be our Fourier transformation. This is going to be our inverse Fourier transformation. Right, and usually from now on when I write it, I'll write this 1 over root 2 pi in front, so it will look something like this: psi of x equals 1 over root 2 pi integral from negative infinity to infinity e to the ikx, or sorry, psi tilde of k, right? You guys get the point. And so, I'm sorry this has been a long video, but it's gotten some really important information. The last thing I wanted to tell you is why this root 2 pi is there. And it turns out, interestingly, that if you have this root 2 pi, so I'm going to erase this at the bottom, hopefully you have it. So as long as you have 1 over root 2 pi, then you can actually show that the integral from negative infinity to infinity of psi of x norm squared dx is equal to the integral from negative infinity to infinity of psi tilde of k norm squared dk, right? If you have this 1 over root 2 pi, if this is the relationship between psi of x and psi tilde of k, then this equality holds, right? And this is our normalization condition. This has to be equal to 1, right? Because as we know that this is rho of x, this is rho of k. You know, you could actually tell me to write it rho tilde of k. I haven't been doing that, but I could. And so this is, right, this is the probability of the particle having a position anywhere from negative infinity to infinity. This is the probability of the particle having some wave number from negative infinity to infinity, right? So this is saying it having any position, and this is the probability of it having any momentum has to be 1, right? This is not necessarily part of the condition, right? But if psi of x is normalized and we put it through this Fourier transformation with the 1 over root 2 pi, then psi tilde of k is normalized, right? So if we have this 1 over root 2 pi, as long as we've normalized psi of x, psi tilde of k is already normalized for us, which is really nice. So that's why we have that 1 over root 2 pi. Okay, I'll see you in the next video.